right, good morning, everybody. So today what we're going to do is we're going to kind of continue with natural selection. Switch scenes. All right, we're going to continue on with natural selection. And one of the things that we had talked about, remember what natural selection is. All right, so I know I've shown this example probably like a dozen times already. You know, you have dark colored rocks and you have these black mice and tan mice. This predatory bird flies overhead, going to see the tan colored mice over the black mice easier. That's going to cause a reduction in population of the tan mice, while the black mice population is the same. And then after a few generations, as the mice start to reproduce, you're going to end up with a higher proportion of black mice for tan colored mice. And then this situation would be reversed if it was on sandy type soils. We'd end up with more tan mice than black mice. So that is kind of our review of what natural selection is. So remember that this trait has to be heritable. Right? It has to be heritable, and it has to be something that allows them to survive over everything else. So they are, I guess, adapted for their environment. So one of the things to remember, Red, is when we talk about evolution, we're talking about phenotype that acts on phenotype. So why is this? Why does it have to be a phenotype? Why does it have to act on the genotype? Well, it has to be on the phenotype because we are actively trying to select against a physical trait. It has to be something that's physical. Whether we use cytochrome B or another molecule to things on the molecular level, that right there isn't going to be as big of an influence as if we had a trait like the black and tan mice, where the tan mice kind of stick out a little bit more than the black mice. And then why does it have to be genotype? Well, because it has to be something that can be passed down. So if you're not able to pass it down, then that is where kind of run into some problems. While with phenotype, this is what it's actually acted against. So it would be like wearing a shirt. Wearing a shirt, yes, that is a phenotype, as in it is we physically can see it, but it's not genetically inherited. That, if that kind of example makes sense. So let's look at a rabbit population. So let's look at this rabbit population. So let's imagine in this we have some brown rabbits and some white rabbits, and brown is the dominant. All right, so brown is the dominant allele and white is a recessive allele. And then a predator like a hawk can see the white rabbits more easily than the brown rabbits against, like, let's say the backdrop of like a grassy field or something like that. So the brown rabbits are most likely to survive. So we have our starting population 50-50. We know that now, is this actually 50-50 looking at the genotype or the allele frequency? No, but it's 50-50 as per the phenotype. So you have 50% brown rabbits and 50% white rabbits. We know that the white rabbits are going to be fully recessive. So they're going to be homozygous recessive. And that's going to lead to then the brown rabbits, some of them are heterozygous. And because of that, it's going to lead to 30%, 0.3 having a dominant trait, and 0.7 having a recessive trait, because you're including all of the ones that are white with the recessive trait, and then all of the heterozygous individuals that are brown. Many of you that turned in the assignment looking at allelic distributions and allelic frequencies, that was one of the things that you kind of struggled with, is just because you say that it's a dominant phenotype doesn't mean that the genotype is homozygous dominant. It could be heterozygous. So you have to look at it kind of in that regards too. So 50% brown, 50% white. We're acting against the white genotype. So we have eliminated from this half. So what survivors are left over? Well, now you have 10 that are brown with mixed genomes, and then you have 5 white left over that have homozygous recessive. So this gives you 67% brown and 33% white rabbits. So 2/3 are brown, 1/3 is white. Notice how your allelic frequencies, though, have shifted, but they've shifted slightly. Does this meet Hardy-Weinberg equilibrium? Well, no, it doesn't, because one of the things with Hardy-Weinberg equilibrium is it assumes that there is no natural selection. And in this case, there was natural selection because a predatory bird was able to kill these rabbits and prevent them from reproducing. So now you have this change in allelic frequency where, because of the number of brown rabbits and each of them having at least one dominant allele, it now shifts this to 0.4 or 40% with a dominant allele, and then 0.6 or 60% with a recessive allele. Even though looking at this, yes, there are more with a recessive allele than a dominant allele, there's still, with the phenotype, there is more that have the dominant phenotype, all right, compared to the recessive, while more have the recessive genotype in this situation. So notice what we've done. Notice, going back to natural selection, we have changed we have selected against the phenotype. So disregard this, all right, disregard this box for now. We have selected against this phenotype, all right, and that has caused a shift to now the population is more dominated by brown rabbits. And because of that, it's caused, now we pay attention to this side, it's caused a shift in our genotype, right? I hope that kind of makes sense. So we've kind of demonstrated this whole thing. So in this example, the dominant allele rose by 10%, while the amount or the number of of the brown phenotype has risen from 50 to 67%. Then we go on to reproduction. Because of the number of individuals that reproduce. Now notice in here, no selection happened from the survivors to the next generation. So this is still the parent generation. This is still the same group as this, just with some individuals eliminated. Notice how our genotypic frequency has not changed. Right? Notice how our genotypic frequency has not changed. Now, given that mating is completely random, we now end up with 65% brown rabbits and 35% white rabbits. Where did this change come from versus this change? Because it is a slight change. You've now added on 2 more white rabbits and 3 more brown rabbits. So where did this change come from in here? Well, it came from how some of these rabbits are, yes, they're going to be mating with some of the dominant ones, but also looking at how the heterozygous individuals, if 2 heterozygous individuals mate and they 4 offspring, chances are that one of them out of the 4 will end up being homozygous recessive. All right, so this is going back to Punnett squares. So we'll go back to paint real quick. Stick with red. So we are using heterozygous rabbit and a heterozygous rabbit. Notice that both of these rabbits are going to appear as brown. They have one brown offspring, another brown offspring that's heterozygous, another one that is heterozygous, one white, homozygous recessive. This is where that white allele survives at, is because it's coming from the parents. Now the thing is, notice you have 50-50 right here. You have 50-50 here compared to these two. This allele will carry on. Now let's forget about this. This guy is going to get selected against him. Right? Let's just pay attention to these. It means you have a 1 out of 3 chance you're going to have a dominant allele. 2/3 chance that a surviving individual is going to be heterozygous. So this allele is still surviving. This is how we end up with no change in our allelic frequency distribution, given that mating is random. All right. And again, if you guys have questions as this goes on, make sure that you are posting to chat so that I can answer them. All right. But this gets into a term that we're talking about called fitness. And this is not what we think about with fitness. So this is not, I guess we'll call it physical health would be a good term for it. All right. This is not physical health. This is not like, you know, if I were to say like Usain Bolt has a high amount of fitness, that's not the same exact thing. All right. So it is not physical health. It is reproductive. Reproductive fitness. So what does reproductive fitness mean? Well, it is how well an organism, I completely spelled that. How well organisms survive and I'm trying my best. Reproduce. Trying my best with this mouse. This thing is unwieldy to use. This is the most comfortable mouse in the entire world, but it sucks to write with. So the emphasis here is reproduce. All right. So plenty of organisms survive. Not all of them survive to reproduce. So it's the number of viable offspring that an organism with a particular genotype will have on average compared to others within that population. All right. Now, remember, survival is one important component of fitness. In order to leave any offspring at all in the next generation, an organism has to reach reproductive age. So looking at those, the brown versus white rabbits, if those white rabbits were killed before they reached maturity, then that would be a negative thing against them. So the brown rabbits had higher fitness compared to the white rabbits because a larger fraction of them survived in order to reproduce. Living for a long period may allow an organism to reproduce more separate times. So yes, while we think about, oh, the parents are going to have one set of offspring, in reality, they're having multiple sets. Now, survival is not the only part of the fitness equation. All right, survival is not the only part. Fitness also depends on the ability to attract a mate and the number of offspring produced per mating. So an organism that survives for many years but never successfully attracts a mate or has offspring has zero fitness, all right, or low fitness. For anyone that's ever that has Mr. McVeigh, he has 4 kids. So one of the things that he always says is that he has a high fitness level compared to myself, where I have 0 kids, which means my fitness is 0. I have survived all right, but my reproduction level is very low compared to McVeigh, who, yes, he has survived and reproduced 4 times, which means that he has a higher amount of fitness than what I have. And each of these traits kind of depends on their environment. So which traits are favored by natural selection depends a lot on the environment. And these are features that make that organism more fit. So in our example, a brown rabbit might be more fit than a white rabbit in brownish grassy landscapes, especially if the predators rely a lot on eyesight. So let's say we had a light colored example. So like there's some places that have like white sand. So if we were in like a white sandy dune, for example, then the white rabbits would probably have better fitness than the brown rabbits because of the ability to avoid predators. And what happens if we eliminate all the predators completely? Well, then the 2 coat colors are considered to be equal fit. All right. So that is always a possibility. There are sunflowers that exhibit that, where they are able to survive in both dunes and or in sandy soils, and also they're able to survive in grassland, wet grassland areas. and they're able to do that with equal fitness. All right, but in most cases, the traits always involve some sort of trade-off, right? There's it has positive and negative effects on fitness. So a particular coat color might make a rabbit less visible to predators, but also might be less attractive at, or also might be less attractive to mates. So fitness is both survival and reproduction. So the coat color is a win if it is able to do both, if it's able to attract a mate and survive, or I guess survive and attract a mate. So an example would be a cardinal, right? So here comes my awesome drawing of bird. There's head and other. Believe it or not, that's actually not too bad. I'm very impressed with that. So we're gonna go ahead and call that a win. Right, that is a win. So we have this cardinal, right? Cardinals are so the males are bright red. Females kind of have like a dirty red color. So if you ever see a cardinal that has like white tinting to its feathers, that is most likely a female. And so the thing is that bright red color is because males have to attract a female. All right, and if this cardinal over here, look, this thing is good, so I'm gonna go all out with it. So if this little cardinal over here, right, if he is trying to attract a mate, remember that he's going to stand out more to predators because of his red coat, right? So that is going to be a detriment to him in one area. I don't know much about predator prey of cardinals. That is a pretty good cardinal. Go ahead and save that one. So that coat color is to attract a mate, not necessarily does it have to do with survival. So remember that the traits have to be a win-win. So for example, looking at the albino peacock that's at the Fort Wayne Children's Zoo, that will not reproduce, even though the white coloring looks really cool to us. It's not going to reproduce because it's not considered to be or it's not made to attract them. All right, so different phenotypes in a population. We're going to start talking about natural selection, how they control genes. So different phenotypes in a population are determined by just one gene. So we look at coat color, that's determined by just one gene. But in many cases, it's determined by multiple genes, and so it's polygenic. We talked about this in class as an example of the Labrador retrievers. There is there's chocolate, and then there is black, and those are the two colors that they can have. Now then there's a second gene that says, does it express that color? And if it has the black trait, which is the dominant trait, but it doesn't express the pigment, then that's where you end up with yellow labs. So yellow labs have recessive traits on pigment, but might have either dominant or recessive for the pigment color itself. It's just the expression of that pigment has changed. So these are called polygenic traits, and they tend to form a spectrum. That spectrum looks like this. So if you plot the frequency on it, and we're going to look at height, number of people, right? So some people tend to be pretty short. Others, there are some that are pretty tall, but for the most part, people kind of fall into what we would consider to be average height. So like myself, I'm 6'2", so I am 74 inches. So if this is 75, 74, I would be right here. Now, there are people that are taller than me, and there's a lot of people that are shorter than me. But if you look at it, I kind of fall into this bracket where most people fall into. And so this is when you look at it, it kind of forms this curve like this. How does it do that? Well, it's polygenic. Sick bird right there. So polygenic traits are where if it's height, J is terrible to use. That would be as tall as you can get. That's as short as you can. So any sort of change in one letter would result in a change in height. So that is what's meant by polygenic, where there's multiple traits that are controlling multiple things. And this is how we end up with this distribution, right? And so what natural selection is, like if we consider this to be the distribution of alleles, all right, so instead of looking at height, think about this as distribution of alleles, this being full recessive and this being full dominant, and then kind of having a range in between. We have to look at the different types and how they can shift that. So there's three basic ways that natural selection kind of influence the distribution of these phenotypes for polygenic traits, and we're going to illustrate that below. So let's use an imaginary beetle. All right, so this beetle is its coat color is controlled by a bunch of different genes. So you have light colored ones on the recessive end, and dark green color ones all the way on the dominant end. So there it is. Stabilizing selection is going to be our first one. So in this, intermediate phenotypes, basically the ones that are in the middle. So I guess regular green instead of light green and dark green, it's just regular green. So you can see what it looked like with the dotted line being the original population. And then instantly there's something that selects against light green or dark green. Let's say that this right here in the center matches up with leaf color perfectly. So if they're light, they'll stick out, and if they're dark, they'll stick out. And so what this does is it tends to push the curve in. So why does it increase? Well, because now you have more beetles that are going to be at this intermediate color. This is sometimes considered to be a better form of selection because if something happens and instantly it is disadvantageous to have the darker color, then you have the light colored alleles in here, and vice versa. You have both light and dark colored alleles in the population. So in this example, green a little bit better camouflaged, so able to fit. The next one we're going to talk about is directional selection. This one is seen a fair bit. So in this example, let's say leaf colors tend to be darker, right? So what this does is this is where one phenotype, one extreme phenotype fits more than the other ones. So think about the rabbit example. In this one, darker colored fits, so there's a shift over. In this example that's on the page, darker colored beetles blend in a little bit more, and that's going to cause selection against the lighter colored ones. This can lead to fixation where you do start to lose out on some alleles, right? It can lead to fixation where you lose out on some alleles. Now notice how it kind of forms this skewed curve where you have this longer tail. And the reason being is because not all of these individuals are eliminated, just most of them. All right. And on top of that, in these, you might still have some of the alleles that allow it or it carries some of these alleles over here in a recessive form, but they might be masked by a dominant allele. And because of that, they are going to pop up more and more and more when it comes to selection. So in this, let's say you have darker colored leaves or vegetation, the darker beetles are able to hide better, they're able to survive, and they're able to reproduce. And so this shifts the curve in one direction. All right, last one. I know this was kind of a quick lesson, but I didn't want to spend way too much time on this. All right, so in this example, both extreme phenotypes are more fit than those in the middle. All right, so let's say that in this you have light green patches of moss and let's say dark green leaves. And because of that, being light in color, you're able to kind of hang out on the moss, and being dark in color, you can hang out on the leaves. And this causes this disruptive selection to happen where you start to select against the medium, where it's more advantageous to have one or the other. And so this is disruptive selection because it disrupts the center. Your mean or your average is still the same. It's still right down the middle, right? So your mean is still the same. It's just you've now shifted your distributions of your population to the sides, all right? So because of this, it kind of diversifies a little bit. But this could also lead to issues because if there is a disruptive selection for a long enough amount of time, it could lead to speciation, which is something that we'll be covering later. All right. I'm looking at that awesome bird. Bird is pretty cool. Because that's the thing is like I suck at drawing on the computer, so I just want to make that. Let me switch over to my camera. Then okay, so kind of going through our summary, natural selection causes this kind of shift in alleles over time. As fitness increases, certain alleles will become common, and then that'll change over time. And remember, fitness in this case is a measure of reproductive success. It's not a measure of physical fitness. If a bird grows arms and is able to lift weights, that doesn't help him if he's not able to reproduce. All right, so survival and reproduction are your measures of fitness. The more offspring that an individual has, the more those parents' genes are going to influence the next generation, which means that that has relative to others who have fewer offspring. So it acts on traits, being it acts on phenotype, but influence type. So thinking about polygenic traits, remember the three forms of selection that we have: stabilizing, directional, and disruptive. Stabilizing pushes more toward the mean. Directional shifts it away from the mean toward one of the extremes. So one of the phenotypes of the extremes are favored. And then disruptive is where you favor both of the extremes and kind of cleave down the middle, where it's pushing the center of that curve down a little. All right, so assignments are posted on PowerSchool. Make sure that you guys are doing that, turning them in. I've been getting them, I've been grading them, I've been putting them in. Nice job on being able to get a lot of that stuff done. I know some of you had limited computer access. Again, we find out more information week after week, so be prepared to for any changes. You'll be making some phone calls today, especially to students who are not doing well or failing. I mean, it's a fair portion of people. I know we need to get those students up. We gotta get them passing so that they don't end up going into next semester having to do this. So if you are failing or you know someone who's failing, make sure you're having them actually on here participating, have them show up to office hours, turn in assignments, all of that stuff. All right. Everything's on PowerSchool, no secrets, nothing hidden. Yeah, that's pretty much all I have for today. If you guys have any questions for on PowerSchool, Cardinal, but if you guys have any questions or anything like that, I'm gonna be over in PowerSchool. Probably gonna be over there in like 15 minutes. I wanna get some stuff done before I head over to PowerSchool. So check or head over to Google Meets. So check PowerSchool for the link. It'll be up. It's on both the homepage and the announcements. So if you have any questions about that, but other than that, I will see everybody for biology. I'll see everybody next Monday. So have a great day. Stay safe.